Welcome to the deep dive. Usually when we talk about building infrastructure, there's a predictable ceiling.
Right.
Think about like engineering a skyscraper. You dig down to bedrock, you account for wind resistance, you reach a certain height, and you just sort of say, well, that is the limit. The materials literally cannot support another floor. But today, we are stepping into the world of AI data centers, and honestly, that predictable ceiling is completely gone.
It really is.
Yeah. We have a staggering stack of sources on the table for this session today. We've got tech analyses on cutting-edge chip design from Mumu.
Oh, yeah, that one's fascinating.
It is. We also have financial reports unpacking power delivery from Big O Finance, a really thorough breakdown of data center optics from the IO Fund, and finally, this just mind-bending Q2 2027 SEC filing from Nvidia.
Yeah, that filing it's something else.
Right. So our mission today is to understand how the sheer speed of AI evolution is quite literally forcing trillion-dollar companies to rewire the fundamental laws of physics in real time.
You know, the word revolution gets thrown around so casually in tech, but what we are looking at here is an absolute architectural overhaul of the physical world.
Yeah.
I mean, we are moving way beyond abstract cloud concepts. We're dealing with the brutal realities of copper wire, thermal dynamics, electrical resistance.
The physical stuff.
Exactly. The biggest players in the industry are racing to solve these physical bottlenecks just so AI can take its next step.
Okay, let's unpack the root cause of these bottlenecks first. Because, well, we have to look at how incredibly fast the silicon itself is evolving. AI is no longer waiting around for human engineers to sketch out the next generation of hardware, right? It's actively accelerating its own design process. Our first source outlines OpenAI's new in-house ASIC chip, codenamed Jalapeno. And to me, this feels like a student taking a test, grading it themselves, and then simultaneously inventing a highly advanced, entirely new grading system while the teacher is out of the room.
I love that. That analogy hits on the core disruption happening here. Because the timeline alone, it shatters industry expectations.
Yeah, tell me about the timeline.
So, according to the Mumu analysis, Jalapeno went from the very start of design to the completion of tape-out in November 2025.
Right.
That was a window of just 9 months.
I need to pause you there, because 9 months is unheard of.
It's crazy.
The standard cycle for a custom chip is usually, 18 to 36 months?
Yeah, exactly. At least a year and a half.
And you mentioned tape-out. And specifically, the source talks about a kawash packaging tape-out. Can we clarify what that actually means for the listener, just so we're all on the same page?
Absolutely. So tape-out is the historic industry term for the final result of the design process. It's the moment the blueprint is frozen and sent off to the fabrication plant to be manufactured.
Okay.
But they didn't just tape out a simple chip, They taped out a CAWAS design.
Which stands for?
Chip-on-wafer-on-substrate.
Okay.
It is an incredibly complex 3D stacking technology. Basically, multiple components are packed tightly together on a single microscopic base. Designing that usually takes armies of human engineers years to perfect.
So how on earth did they compress a multi-year, highly complex 3D puzzle into 9 months?
Well, by fundamentally changing the workflow. OpenAI heavily integrated their own models into the engineering process.
Like using ChatGPT to build a chip.
Basically, yeah. They used GPT Astra and an internal version of Codex, not just as code assistants, but as structural co-pilots.
Wow.
For instance, engineers used the AI to rapidly evaluate millions of spatial configurations for the logic gates. This allowed them to reduce the physical area of the SIMD units by 8% and the matrix engines by 10%.
And SIMD stands for single instruction, multiple data, right?
That's right.
It's the part of the chip that does the heavy lifting for parallel processing. But why does shrinking them by 8% matter so much? Is it just about saving physical space on the board?
No, it's about physics and performance. When you shrink the physical area by 8%, the electrons literally have a shorter path to travel.
Oh, I see.
Yeah, which reduces latency and lowers the heat generated. It also means you can pack more compute cores into the exact same silicon footprint.
That makes a lot of sense.
And beyond spatial layout, they use the AI to write complex hardware kernels, with some of the code reaching 3,000 lines.
There are 3,000 lines of hardware code written by the AI.
Yeah. And the AI-generated code was running up to 1.8 times faster than what top human engineers had previously implemented.
That is wild. How does the AI beat top engineers at that?
Because the AI could spot optimization patterns humans simply could not see in the dense mathematics.
Wow. And the performance benchmarks they achieve with this AI-assisted design are just They're wild. When tested on the GPT OSS 120B model, Jalapeno pushed 1,459 tokens per second.
Yep.
And to put that in perspective for everyone, NVIDIA's flagship GB200 chip hits about 535 tokens per second.
Right. It's almost 3 times faster.
And Jalapeno is accomplishing this while drawing only 700 watts of power. The total cost of ownership, the TCO, is down to a stunning $1.56 per chip per hour.
What's fascinating here is that the efficiency comes from a major architectural shift. The design philosophy of Jalapeno is to eliminate fixed latency.
Okay, how so?
Well, instead of relying on traditional complex memory hierarchies, Jalapeno binds its compute cores directly to HBM4 memory.
High bandwidth memory, generation 4.
Yes. So think of older memory architectures, like taking a long walk down a crowded hallway to retrieve a file from a cabinet.
Okay.
HBM4 is like having a high-speed, dedicated elevator integrated directly into your desk. The data retrieval is nearly instantaneous, and they paired this with out-of-order execution cores.
You know, out-of-order execution always sounds counterintuitive to me. How does processing things out of order actually make a chip faster?
It's a great question. In a traditional in-order processor, tasks are handled like a strict assembly line.
Okay.
So if step 3 is delayed because it is waiting on a piece of data from memory, steps 4 and 5 must sit idle. The processor wastes time waiting.
Right, the whole line stops.
Exactly. Out-of-order execution uses a component called a reorder buffer. The processor looks ahead at the incoming instructions. If the data for step 5 is ready before step 3, the chip goes ahead and executes step 5, holding the result until step 3 catches up.
Oh, wow.
Yeah, it dynamically keeps all the hardware busy all the time. Furthermore, they opted not to use prefill and decode separation, or PDD.
I actually found this part of the source particularly interesting. To visualize the lack of PDD, I try to imagine a coffee shop.
Okay, I like this.
In a traditional setup, you have a dedicated line just for taking orders and a separate line just for making the drinks.
Right.
That works great until a tour bus arrives where 50 people want to order, but no one is ready to pick up a drink yet. The baristas making the drinks are standing around doing nothing while the cashier is completely overwhelmed.
That's a great way to look at it.
By abandoning that strict separation, Jalapeno creates a homogeneous resource pool. Every worker in the shop can instantly switch from taking orders to making coffee, depending on where the bottleneck is.
And that flexibility is critical because real-world AI production environments have constantly fluctuating concurrency levels.
Right.
By keeping the resources adaptable, Jalapeno can pivot instantly between a sudden spike in user prompts, which are highly sensitive to latency, and high-throughput background processing.
And the reason we're spending so much time on Jalapeno is that it proves a massive industry theory. For years, the prevailing wisdom was that NVIDIA's CEDA, their deeply entrenched software and hardware ecosystem, was essentially an impenetrable fortress.
Absolutely.
But this proves that an AI software company, utilizing its own models, can build a highly competitive, custom inference chip from scratch, shed all the legacy design burdens, and do it in record time.
The technological flywheel is spinning faster than anyone predicted. However, this blistering pace of silicon evolution brings us to the first major physical consequence.
Here we go.
Jalapeno and the next generation chips like it are incredibly dense and thirsty for power. When you arrange tens of thousands of them inside a data center, you hit a hard wall of physics.
The power bottleneck. Let me try an analogy here to ground the concept, and you tell me if I'm on the right tracks.
Sure.
If I plug a high-wattage hairdryer and a microwave into the exact same kitchen outlet, I blow a fuse. The wiring simply can't handle that much current at once. Is that basically what happens when you try to draw thousands of amps of electricity across a modern server motherboard?
That analogy gets us part of the way there, but we need to adjust it slightly to understand the true engineering nightmare happening here.
Okay, adjust away.
A blown fuse in a house is a safety mechanism tripping to prevent a fire. In an AI server, the issue is not a safety breaker. It is the fundamental nature of the I-squared-R law.
Ah, right. Current squared times resistance.
Precisely. We are witnessing the failure of traditional lateral board-level power delivery.
Lateral meaning horizontal, right?
Yes. Historically, the voltage regulation component sat around the outer perimeter of the processor. The power traveled horizontally across the motherboard's copper traces to reach the core.
Okay, that makes sense for older chips.
Right. But today's AI chips operate at very low voltages, around 0.6 to 0.8 volts. To achieve the immense total wattage required, the current must skyrocket to thousands of amperes.
Wow.
So when you push 3,000 amps horizontally across a few centimeters of copper, the resistance turns a staggering amount of that electrical energy directly into heat before it ever reaches the processor.
Because the power loss scales quadratically with the current.
Exactly. The data from TSMC illustrates the severity. Traditional board-level power delivery network, or PDN, resistance hovers around 90 to 140 microohms.
Okay.
In a modern AI server cluster, that translates to 20 to 30% of the total system power being wasted entirely as heat along the copper traces.
Wait, 20 to 30% is just lost as heat.
Just lost as heat.
Which is a catastrophic inefficiency when we were talking about gigawatt-scale infrastructure. You are literally paying millions of dollars to heat up tiny strips of copper. And then you have to spend millions more on advanced liquid cooling just to remove that useless heat.
Yeah. It's a vicious cycle, and it's forcing the industry into a structural revolution called vertical power delivery, or VPD.
Right.
To stop the lateral loss, engineers are moving the voltage regulators directly beneath the processor. Instead of traveling across the board, the current flows vertically, straight up into the core.
But what does that actually look like physically? Like, how do you put a voltage regulator underneath a microscopic chip? Does the motherboard just get thicker?
Well, in the short term, yes. The fastest route to market is PCB VPD, which involves soldering power modules to the underside of the printed circuit board and routing the pins straight through the substrate.
Oh, I see.
This cuts the physical travel distance from centimeters to mere millimeters. It slashes the PDN resistance down to just 10 to 15 microohms, reducing power delivery losses by up to 95%.
That's a massive drop, and I assume it frees up all that prime real estate around the edge of the chip too, which engineers desperately need for packing in more of that HBM4 memory we talked about earlier.
You hit the nail on the head. The operational benefits are immense. It also allows the power supply to react much faster to the sudden, violent load fluctuations that occur the millisecond. An AI model begins processing a complex prompt.
Right.
But PCB VPD is just the beginning. The medium to long-term future relies on SIVR.
That's not
They're substrate integrated voltage regulators. That's where the regulation components are built into the actual foundation the chip sits on. And eventually, the industry will move to in-package IVR, embedding the power regulation inside the silicon package itself.
Here's where it gets really interesting on the business side. This physical necessity has sparked a colossal financial land grab. Our source from Big O Finance highlights this frantic sequence of mergers and acquisitions that unfolded between May and August of 2026.
Yeah, the frenzy.
Analog Devices bought Empower Semiconductor. Infineon acquired C2I. Nvidia swallowed up Claros. The world's largest semiconductor conglomerates are devouring startups just to own the patents for vertical power delivery.
They're making those acquisitions because they know the traditional architecture is dead. Intel, AMD, Google, Nvidia, none of them can build their next-generation servers without implementing vertical power delivery. The underlying physics demands it.
So we figure out how to power these monster chips by feeding them vertically from underneath. But resolving that bottleneck immediately creates the next physical nightmare.
It always does.
Right. How do we connect these chips to each other? A modern AI cluster relies on thousands of GPUs communicating in perfect synchronization, sharing data horizontally. But our old friend, copper wire, is failing us again.
It really is. Copper is hitting an impenetrable ceiling regarding data transfer bandwidth.
Let's try another analogy here. Pushing 200 gigabits of data per second through a standard copper wire feels like trying to shout a highly complex mathematical equation across a crowded, noisy football stadium.
I like that.
Over a very short distance, the person next to you hears the equation perfectly. But if you try shouting it to someone across the field, the sound waves just degrade into unintelligible mush.
Exactly. The concept of signal integrity degradation maps perfectly to electrical cables. As you scale up the bandwidth, the amount of data pushed per second, the effective distance a copper wire can carry that signal without corruption shrinks dramatically.
Okay.
Let us look at the specifications of Nvidia's NVL576 cluster. This architecture links 8 heavy server racks together into one vast, coherent processing unit. Physically, that setup is nearly 5 meters wide.
But at 200 G lane speeds, the active electrical cables, the copper AECs used to connect everything, reach their maximum physical limit at roughly 3 meters.
Right.
Copper physically cannot carry the data across the room fast enough without the signal degrading into noise.
And that physical barrier is forcing the next architectural leap. co-packaged optics, or CPO.
Moving from electricity to light.
Exactly. When electrical signaling fails over distance, you must transition to light. Fiber optic cables can carry staggering amounts of data over kilometers with virtually zero signal degradation.
Right, fiber internet is the thing we all know.
Yes. However, traditionally, using optical transceivers meant plugging a separate module into the front panel of a server switch.
Which introduces a whole new problem, right? To use those traditional pluggables, you need a digital signal processor, a DSP.
And DSPs are incredibly power hungry. When a degraded, noisy electrical signal arrives at the edge of the board, the DSP has to execute complex mathematics to clean up and amplify that signal before it can be converted into light by the laser.
So you're spending power just to clean up the mess that the copper made.
Exactly.
The IO Fund report notes that Nvidia is throwing billions of dollars at bypassing this very problem. They made $2 billion equity investments in both Coherent and Lumentum. Those are the companies manufacturing the lasers and silicon photonics for these advanced networking systems.
Because co-packaged optics is the elegant, definitive solution. Instead of sending an electrical signal across a long board to a pluggable transceiver, CPO takes the optical engines and embeds them directly into the same package as the switch ASIC.
Oh, wow. So by moving the laser right next to the processor, the signal doesn't have time to degrade.
Exactly.
Which means they eliminate the need for those power-hungry digital signal processors entirely.
The efficiency gains are tremendous. By shortening the electrical path before the conversion to light, the signal loss drops from 22 decibels in a traditional pluggable system down to just 4 decibels with CPO.
That is a huge drop.
It is. This delivers up to 5 times better overall power efficiency and significantly lowers the latency of the network.
And latency is the ultimate battleground of the future. I mean, the projections in our sources indicate that inference, the actual execution and daily use of AI by consumers and enterprise agents, is going to overtake training by 2030.
Definitely.
We're looking at 93 gigawatts of global data center demand just for inference, compared to 62 gigawatts for training. When autonomous AI agents are executing real-time workflows in finance or medicine, they cannot wait for signal lag.
If we connect this to the bigger picture, the necessity of low latency explains why Broadcom is racing so aggressively into the CPO market alongside Nvidia.
Oh, what are they doing?
Well, they recently published testing data with Meta demonstrating a 5 times improvement in serviceable failures compared to traditional pluggable transceivers.
Wow.
Their CPO systems ran for 15 million hours with 0 unserviceable failures. Copper might be cheaper to install today, but when the industry standards move to 200G and beyond, co-packaged optics will be the foundational bedrock of all AI networking.
Okay, let's take a breath and look at the whole board here. We have OpenAI building remarkably efficient, out-of-order execution chips that directly threaten the established hardware ecosystem.
Right?
We have the physical infrastructure of power and optics undergoing a complete metamorphosis because the legacy physics simply will not scale.
Yeah.
You might assume the current undisputed king of the hill, Nvidia, is sweating right now. So what does this actually mean for their business? Let's open up their Q2 2027 SEC 10Q filing.
Oh boy.
The numbers inside are dizzying.
The scale of capital is almost hard to comprehend. Nvidia reported revenue of $96.2 billion for the quarter.
$96 billion.
Yeah, a 106% increase year over year. Net income reached $59.7 billion. But, anyone analyzing the sector knows the historical revenue isn't the most vital part of a 10Q.
No.
The true story is found in the forward-looking commitments.
The jaw dropper.
Yeah.
NVIDIA lists $279 billion in supply and capacity commitments. And when you factor in their cloud agreements, equity investments, and capital expenditures, their total future financial commitments hit $366 billion.
We need to contextualize what $366 billion in future commitments actually buys. Nvidia is no longer just a fabless company designing chips and hoping the supply chain holds up.
Right.
They are locking down the raw materials of the global digital economy. That money is securing future manufacturing capacity at TSMC. It is buying up the global supply of HBM memory from SK Hynix, and it is financing the global rewiring of electricity and data we have been discussing.
Unbelievable.
They reported $23.7 billion in gains just from marketable equity securities, with another $36.9 billion locked up. They are basically acting as the central bank of the AI infrastructure boom.
But wait, here is where I really have to push back, because this filing reveals what looks like a glaring contradiction.
Okay.
The document explicitly states that Nvidia entered into SB Energy guarantees capped at $105 billion for an open AI-related AI campus, with projects coming online starting in fiscal year 2029. But we spent the first part of this deep dive talking about OpenAI building the jalapeno chip, specifically to challenge Nvidia's hardware monopoly. Are they rivals or are they partners? Why on earth is Nvidia financially guaranteeing $105 billion in real estate and power infrastructure for a software company actively trying to disrupt their core business?
This raises an important question, and that paradox is the defining characteristic of the modern AI economy.
Make it make sense.
Okay, yes, OpenAI proved they can engineer highly competitive silicon. But their internal demand for sheer computational power is so astronomically high that they cannot possibly manufacture enough jalapeno chips to satisfy their own roadmaps.
Oh, I see.
They still desperately require NVIDIA's upcoming Blackwell and Rubin infrastructure to train their frontier models.
So the global demand for compute is vastly outstripping the supply of any single architecture, even a highly optimized in-house design.
The demand is insatiable. For NVIDIA, guaranteeing $105 billion in infrastructure for a potential disruptor makes perfect strategic sense.
Because they're the customer.
Because OpenAI is simultaneously their largest customer and the primary catalyst to the entire software ecosystem. OpenAI's advancements force every other tech giant to buy more NVIDIA hardware just to keep pace. Financing their infrastructure ensures the rising tide keeps lifting NVIDIA's ships.
It is a phenomenal web of dependencies. If we step back and recap the journey we've taken over the last 15 minutes, well, we watched the entire physical stack transform.
We really did.
We moved from AI models successfully acting as engineering co-pilots to design chips in 9 months, to the realization that copper traces are melting, so the industry must route power vertically through the motherboard, to the acceptance that electrical cables are too noisy, so we must embed microscopic lasers directly into our switches. And it all culminates in a single company anchoring a third of $1 trillion supply chain to manifest this new reality.
Bringing it back to the daily experience of the listener, it reframes what happens when you interact with this technology. When you type a simple prompt into an AI model today, you are initiating a cascade of physical events. You are firing embedded lasers, you are triggering vertical power regulators delivering thousands of amps in milliseconds, and you are activating execution cores that dynamically reorder logic.
All in the blink of an eye.
Exactly. All functioning within a data center that literally required breaking and rewriting the physical boundaries of engineering, to answer your question.
Which brings me back to the skyscraper analogy we've started with. We used to rely on predictable ceilings. We understood the boundaries of corporate competition and physical materials. But if a hardware giant is financially underwriting a $100 billion power and land guarantee for a software company that is actively designing rival silicon, are we witnessing the end of traditional corporate rivalry?
That's a great question.
Perhaps in the era of 10-gigawatt clusters where you have to engineer new physical paradigms just to keep the lights on, the capital requirements are so immense that true competitors no longer exist. Maybe we have simply entered an ecosystem of mutually assured compute.
The ceiling is gone, and the rules of engagement have been completely redrawn.
Something to mull over the next time you casually ask an AI to summarize a recipe or draft an email. Thank you all for taking this deep dive with us today. It is a thrill unpacking the shifting landscape with you. Keep questioning those limits.